Okay, again, welcome to this afternoon session. It's for lab for physics 4C. And the lab today is, let me find it first, modules. It's on standing waves. So that lab 3. Let me pull the file, download it on my computer. Open with Acrobat. And let me move it to this screen because I've had difficulty before in the past sharing from the other screen, especially when I need to write. And let me go back into here, share, and it's the resonance and standing waves. Okay, like any other lab, basically you guys need to read through the instructions of the lab, go through the rubric. The rubrics are detailed, so this is again another reminder for the same thing that we've been doing now. This is the third lab, so you guys now know the routine, okay? So this lab is on standing waves. This is the chapter 15 and to some extent also 16. So so again, if I open the lab and I look in the bottom, it tells you when the lab is due and basically how it's graded. It's very important that you guys go through these steps. Now it's interesting for this specific lab, and you will see exactly that is, some of the questions are broken into 3 components, 3 parts, part A and B and C, and each one of them receives its own points. Some of these components receive 3 points and some of these components receive just 2 points. So you really have to pay attention to some of these questions and how they are graded, okay? And then we have also what is unique about this one. We have some 1-point questions basically, and that is to measure the length and measure also the time, and also for the case when the ends are open and when the case are loose and when the case are actually fixed, and do some calculations and answer the questions and finally the conclusion. So the total lab points are 56 points. Hopefully you guys went through the rubrics. Go through the rubrics all the time for any assignment I give. So, okay. So again, the name in here, please read through this, go back through the lecture and try to understand what we're doing in here in terms of standing waves and also in terms of resonance. It is important that you know exactly what the objective is. So if you're not sure, it's a good idea to leave it and come back to it later on. Make sure it's filled though, okay? That's an interesting point in here for damping versus dampening, okay? Dampening something is getting it moist, whereas damping is actually killing something, basically attenuating. That's another word that is used actually when it comes to vibrations and oscillations and waves. The wave basically over time decays and goes to 0. That's another word, decay, attenuation, and also damping is the same thing. They're all meaning the same thing, that the waves basically over time they go down. Here is the wave equation. This we have seen it in the case of string. I did not really derive this equation for the sound, but I assume that you guys can go and read through that complicated basically derivation from Mr. Feynman. So again, this is the same wave equation that you guys can come back to it. So at this point, make it, it's like when you're doing a problem in physics, and I know some of you are sitting in Math Physics 4B, and we'll be doing that when it comes time to it down the road when we get into physics, when it gets into chapter 32. We will do the electromagnetic waves, and we will see that they also obey this very same relationship. Okay, we'll get into something similar, okay? Hopefully you have seen so many partials so far that this doesn't scare you as much because it's just derivative of with respect to one variable when the other one is constant, because this displacement here on the string can go up and down. So in this case, it can go up and down in time and at any given point, but that point actually, the behavior of the waves travels from point to point. So there is a spatial dependency and temporal dependency expressed by this displacement in the y direction, in this case with respect to the length of the string and also the time, okay? Of course, when I have 2 waves, one of them going to the left and one of them coming to the right, and they meet, and if they happen to have the same frequency, But of course, the going to the left has omega kx minus omega t, or going to the right, I should say, going this way, to my right, and to your right too. So we're going to have kx minus omega t. The one that is going to your left is going to have kx plus omega t. And if you work the trig identity in there and work out your basically cosine this plus that, cosine this minus that, you add them correctly with the proper behavior, because as it reflects, it's going to change direction, then you're going to get into this expression. And this expression is very easy to verify that indeed it's a solution. All you have to do is, and that's of question 1 actually, is to take its derivative with respect to x twice. When you take its derivative with respect to x twice, you're going to pull 2 pi over lambda squared, the whole thing squared. You're going to pull 4 pi squared over lambda squared. Because this is respect to x is constant. This is a constant anyway, all the time. So the sine, when you take its derivative, is going to be a cosine. When you take the derivative of the cosine one more time, it's going to be a negative sine. So you're going to end up with a negative sine, but this coefficient every time is pulled again, okay? Because when you take a derivative of something times x with respect to x, you're going to pull that something first, and then multiply by the derivative of sine in this case, which is a cosine. So when you take the derivative of the cosine one more time of that something times x, you're going to pull that something again with a negative sign. Okay, this is basic calc stuff, okay, that you guys can do. What the partial in here means is ignore this temporal behavior. Forget it. We're just focused on the spatial behavior. Now, when it comes to this term, we're going to do the same thing, the derivative, but with respect to t. That means this guy is constant with respect to t, and this is constant anyway. So again, the derivative of cosine of something times t with respect to t, pull that something first, which is 2 pi f, and then change the sign from cosine to negative sign and leave the argument. So it's going to be negative 2 pi f times sine of 2 pi ft. Okay, that's the first derivative, but you need another derivative to get to the second derivative. So it's going to pull that something, which is 2 pi f again. So we end up with 4 pi squared f squared times the same stuff as you're looking at. And you plug into this equation, and all of a sudden you will end up with 4 pi squared over lambda squared minus 1 over c squared, or 1 over v squared, times 4 pi squared f squared, and then this stuff, which is identical, which you cancel side by side, because you would want this equation to be true all the time, meaning t doesn't matter, so you cancel t, and you want this equation to be true everywhere. That means x doesn't matter, so you cancel with respect to x, and you would want to cancel with respect to the amplitude, because you assume the amplitude is not 0, because if it's 0, then you don't have any solution in here. Obviously, y equal to 0 is a trivial solution to this equation. So you don't care about the trivial solution. So that is actually the steady string. If the amplitude of the oscillation is 0, that means the string and disturbed before the wave started going in it. So again, just taking these derivatives and plugging them in there, we should verify that v equal to lambda f. Okay, so that's question 1. And then question 2 now, this string is fixed from both ends. Okay, if it is fixed from the both ends, this thing in here I forgot to fix is just n equals to 1, equal to 2, n equals to 3. These are the different standing modes because it's fixed from both ends. One way is if the wavelength is twice as much as this length. And this is condition number 1. Condition number 2 is the wavelength is exactly equal to 1 full length. And condition number 2 is the wavelength is actually, what is it, 2/3 of a full length. And condition number 4 is that the wavelength is what? 4 over 2L basically. That is, it's half the whole length, okay? And so on and so forth. Lambda is 2L over N, I'm sorry. So this is a formula for all the different modes basically that we found in lecture, okay? Put N equals to 1, you will find lambda 1 is equal to 2L. Put N equals to 2, you will find lambda 2 is equal to L. Put N equals to 3, you're going to find lambda 3 is equal to 2L over 3. Put lambda N equals to 4, you're going to find 2L over 4, which is L over 2. That's halfway for this string. That is actually a full length, and so on and so forth. Now, you have to be careful. If we did this lab in the laboratory, you're not going to see this big amplitude. The big amplitudes are just for illustration purposes only, so that you see them. In the lab, you will see hardly this string buzzing, I mean, outside of the straight line, okay? So if we did this line, I mean, probably the first mode, you're going to find it very, very clear. But as you start moving around and around to the higher and higher modes, the string will actually have little room for it. So, and we used to do this lab, and it's a lot of fun. Unfortunately, this is the best we can do right now in these situations. This is the so-called dispersion law. This is exactly what you have proven in this case, except for specific values of lambda and specific value for f, because each and every one of these lambdas correspond to its own f. So that the velocity of the wave, which is constant, which is equal to the square root of t over mu in this case, where t is the tension. T is the tension. I know I used the letter T in letter F for in the lecture, because I didn't want to confuse it with a period T, but actually this is typical. The value of the tension is the letter capital T, okay? Assuming that you guys make a distinction between the T being tension and the T being period, because the period also uses a capital T for it. But it's not going to be used here. We use the frequency to refer to the time. The frequency is 1 over T, but we don't refer to it, at least in this calculation here, as opposed to little t, which is just time, okay? So again, we have the different frequencies in this case. Now, I know I didn't do this in lecture, but I expect you guys to see that if it was a string that is free from one end, then that is going to be an empty node, and it's a node on the other case. So this is actually not even a half wavelength. This is a quarter of wavelength. So imagine with me that this extends so that it vanishes in here. That is half wavelength, and then it goes to the bottom and then goes in here. So the full wavelength will be here. That's why you see 4 in here when it's an open question, okay? So again, you're supposed to go through the lecture if you have difficulty with this one, or maybe we can discuss this one on Wednesday. If you have the difficulty, please look at it. Now, here is the link for the actual simulation for this lab. If you click on it, it's going to take you to the simulation. So I'm going to click on it, and when you hover with it with the mouse, it's going to give you the link if you're not sure. The link is https://fat.colorado. This is from the University of Colorado simulation. So I'm going to click on it. I'm going to allow, and it's going to open a simulation. So I'm going to stop sharing that screen and share with you how it looks like when you guys open it. Share this screen. Okay, so this is the simulation. The buttons you need to be familiar with up front. Pulse versus oscillate, okay? Pulse versus oscillate. So first of all, let me go to manual. This is a button that is going to be very critical for your steps in here. It's a good idea to click it to stop. Right now it is stop mode. It's not playing. So if I go to oscillate, nothing is happening. If I go to pulse, nothing is happening, okay? So because it's paused. Even if I go to pulse and kick the pulse, so right now, it's going to send me the wave in here, okay? Because it started this one immediately. So if I pause it, it's going to start it immediately. So let's pause it again. It's paused in this situation. If you're not sure where you are, because you see that this string in here is kind of not exactly with the vertical, with the horizontal. All you have to do is just hit reset or restart. So that resets these values in here for you. Most of the experiment for this lab is with no damping. This is what I was talking about here, for damping and no damping, okay? And some other probably labs, we might have to do the damping in here, but it's fun without it still, okay? So imagine with me that we're gonna create a pulse of a given pulse width of 0.5 centimeters, of a given height, which is 0.75 centimeters, not a full centimeter. So, and the tension, we can adjust it to high or low depending on how we want. There is no specific value for the tension in here, but at some point you're supposed to find the velocity of the wave as it travels. I'm gonna start it and see how it goes. If I look at it this way, the wave was in here and it's in this shape and it's traveling to the right, okay, on the screen. So this is a right traveling way and it's pointing up, okay? If I continue the play, let's slow down the motion, okay? Slow down the motion, meaning that so that we have control over this. So it's going to hit in here. This point cannot move. So it's going to reflect the wave and it should come from the bottom. Okay, as described. Okay, so now it's moving back to the left. So it has changed. It's not kx minus omega t. Instead, it's kx plus omega t. Not only that, but the amplitude has flipped. That's why I did a minus in the lecture, if you guys remember. The lecture in here, for the lecture, we had to invert the when it comes out of phase by a value of pi. I want you to remember this experiment because down the road we're going to be doing optics, and also we'll have basically light shine on a surface, and light, when it shines on the surface, it reflects back, and it's going to produce for us images on the surface, basically the mirror. Okay, what happened on the mirror? But what happened to the phase itself? It's going to be actually flipped by a negative sign. So that negative sign is critical down the road when we're studying light optics too. So this phenomenon is important. It relates to light. Okay, too. Because this point is fixed, and you can think of it as this wave is coming this way. There is an imaginary wave coming from the bottom to keep this point in its place. So by the time this one is moving in the opposite direction, this one will go. The one that was in the imaginary space will start to appear in here. And the one that was traveling to the right actually will continue to the imaginary point in here and move on, imaginary part of the string. So that is one way of thinking about it. This is both ends are fixed. So this is what we mean by fixed, okay? And these are some of the key things in here. If I stop this, if I reset this, I'm back to where I started from. And I need to pause this. Right now it's paused. Okay, it's not playing. So if I go into the oscillate, it's oscillating. It should be oscillating once I start the play. Okay. The frequency right now is at 1.5 hertz. I can change the frequency, or I can go to a big value. Let's say, for example, I want 2.3. So I can go around it and just go with the mouse, with the clicker in here one way or the other, and it takes me to the right place where I need to be. So if you're asked to go to 3, that's easy. If you're asked to go to 0, that's easy. But if you want to find, for example, 0.75, so come just close from it and start using the mouse to go around it. Okay, it's a good idea you start playing with this thing in here to understand how this works. So this is the frequency. Frequency of what? Of this pulsating, oscillating, basically end. So as this one is spinning, it's spinning actually with this frequency right now. It's 1.6. Okay, it's 1.13. But nothing is happening because actually I did not start this one in here. The end is fixed, and I'm going to go in slow motion, so I will see it, how it's behaving at this frequency right now. It hits, it reverses, and now I have waves on this string in here. Okay. Obviously, there is no damping in here, so it's just whatever you're looking at this motion. In normal speed, this is how it's going, okay? But sometimes it's a good idea to slow down things for you, especially if you're going to be measuring time and things like that, and sometimes you will. So you will need the ruler and measure the length of the string. You will need also the timer and to keep track of the time, okay? So let me restart. First of all, pause it, restart. I'm going to start the time. As you can see, the time has been started, and you can see, we can tell that it started because I have this button here to stop it. But no clock is being kept by the timer, because kept track by the timer, because there is the whole play is paused. So if I start it now and I want to find how long it takes to go to the other end only, I pause it right here. It's 1.25, or I pause it here, whichever way I want to. So in this case, I have 1.25 seconds for it to go from one end to the other. I can calculate the speed of the wave at this point, okay? So at some point, you're going to be comparing the measured value of the velocity versus the one that you measure with the timer and also with the ruler and so on and so forth, okay? So let's reset this. It's paused right now. I can tell it's paused because of this fact that I can start it. I'm going to change the end now to a loose end, okay? And see what's going on, or no end. No, let's keep it with loose end. No end, basically the wave will go forever and ever and ever, okay? So let's keep it with a loose end. Loose end in here, that means that if I go back to the pulse, okay? Let me remove the timer and the ruler. You will see that the reflected wave should have one way. Okay, so let me pulse it. Okay, so as you can clearly see, it's moving to the left, similar to the first one. But in here, this point will be free to move up and down. So as it moves up and down, it's going to be reflected also up and down. So again, and the wave is traveling to the left now. Okay, so this is your entire lab basically. Pay attention to the pulse, pay attention to the amplitude, pay attention to the damping when you start this one. Pay attention also to these rulers and this ones. Pay attention critically to this one if you're going to be measuring things. This is the fixed end, this is the loose end, and everything else in between. Any question about this navigation thing for the entire lab? I hope that you guys can come in here. That's part of your task anyway, is to click on the link, go there and play with it and make sure you understand what each and every one of those buttons mean.
Makes sense.
Okay, very good. It's intuitive enough, hopefully, that you guys can go through it. Let's continue with this PDF file for the instruction for the lab. Okay, so we'll use this animation. This link was embedded on Canvas. Oh, I forgot to embed it on Canvas. It's fine. I'm going to embed it right now. Okay. Okay, where is it? And of course, I lost the code. It's fine. I'm going to get it later on and embed it in Canvas. It's not going to work because I tried it in the past. Canvas does not allow you to have this this stuff basically properly working. So if you have problems finding it on the internet, please let me know. Okay, that is the key thing in here for this lab. I want you guys really to get this thing. So if for some reason you don't have access, please let me know as soon as possible so that I can fix whatever. The thing with it is, you really need internet for this one. I thought that we can download some sort of a Java file and maybe give you the Java file on your computer, but in that case, you really need to have a Java also installed, which is probably down the road. We might need that too. Java is not JavaScript, by the way. Java, you need Java applet to be, Java actually a runtime to be installed to run an applet like this one. So once we get to that point, if we need Java installed on your computer, I will let you know. I'm hoping not to do that. I'm hoping that you still have just with a browser, you can do these things. If not, then I will let you know what needs to happen for that to be done, okay? It is a good practice to explore online simulations first before starting the answering the actual questions in this lab. So that's basically what I was doing with you guys, is basically going through the entire thing. I hope that you guys will spend your time on your own to do these things. For this part, select pulse. So we're going to start with pulse, not oscillate. Fixed end, remember that end to be fixed. The damping to be none, no damping whatsoever. And the amplitude to be 0.75 centimeter of the pulse. And the width of the amplitude to be half a second, okay? Once ready, click on the pulse, you know, that green thing for the pulse to start, okay? And now question, observe the wave and draw a snapshot, y as a function of x with t fixed, okay? So basically freeze time. Like, we pause the play if you want to, and draw it, okay? For the traveling moving from left to right. So here from left to right. So this is the right traveling wave. This is kx minus omega t. Please label things, okay? I know you can draw in here. So if you're going to attach, and most likely that's what you need to do. If you can draw with this one in here, oh man, I can do it with the previous version of the PDF, and now this one I really don't. How do you add comments in here? Comments. Because that's how it used to be. And no, that's a sign. I don't want the sign. I want just the comments in here. And where is the tool? Is it this one? Yep. So that's probably one way of doing it. Yes. Traveling this way. So if I'm doing it, this is the velocity of the wave. Okay. And this is the stationary string. This is the end that is fixed. Okay. And this is the source of the pulse. Okay. So this is a good enough drawing. The one that came back, at least according to my simulation, this is the fixed end. It's traveling this way. Okay. So you have to be clear into how that looks like and so on and so forth. This is the pulse. this is about half a second. The distance between this one and this one, basically that is the inverse of that is going to be the frequency. So frequency of 2, and the amplitude is about 3/4 of a centimeter. Okay. Again, I'm not. If I do it by hand, it's going to be a lot better than this pen in here, because actually I'm not even writing with a pen. I'm writing with a mouse, which is terrible. Okay. So that is basically part 1, part 2. This one is worth 3 points. This one is worth 3 points. The bottom line is worth 2 points, and describe how the motion of the string changes with time. So you're going to go from here, how the string behaves, and so on and so forth. Is this easy enough? This question.
Yeah.
Okay, it's a lot of these questions are so intuitive. I'm hoping that you guys can do them. Okay, so let me go back, finish this. To just describe it, this reflection is very important, as I'm saying in here. This is a reflection actually on a fixed end. Okay, again, the instruction in here, keep the pulse. You do the same thing, click on the green one, but this time is actually loose end. So since Micah just joined us, just do that again, okay? Just to make sure. What is the, why is it still in the commenting thing? And let's close that commenting nonsense stuff. And go back into the link. So we're gonna do, oh man, it was open already, the link, so there was no need for it. Again, stop sharing that. Let me share with you this one. So let's reset everything. We're still doing pulse. We're going to go to the loose end now, they told us. Keep this amplitude, keep that one, and we're going to do the same thing. So again, we're going to start it right now. It's paused, but it's going to start immediately after we start the pulse. So, and it's in slow motion, okay? So I'm gonna describe this behavior, how the wave started from here with this shape and kept its shape all the way throughout, okay? So that's my description. In the drawing, I have to draw this shape. Now, once it hits the end that is loose now, it's not fixed, it's going to be loose. The reflected wave in this case will have the same phase because it's going to be up also, and it's going to be the same shape because I have no damping. If I have damping, it's going to be less amplitude, okay? So as it's coming back, stop. So this is the wave now is traveling from right to left, okay? So if I mathematically want to describe it as kx minus omega, kx plus omega t, okay? Because it's going to the left and it's the same shape. And the only reason why I see the amplitude stays 0.75 centimeters is because I have no damping. If I add damping, as a matter of fact, this thing starts to decrease in magnitude, as you can clearly see, okay? The damping will kill everything. As a matter of fact, I put so much that in slow motion, it looks like it's not moving. In normal speed, it's actually killing everything. So the string will come to rest, actually, okay? So hardly anything. This is tremendous. It's like you're having a big, basically, a string made out of probably heavy iron, and you want to create a pulse on it on one end. That's not good, okay? So this entire thing has no damping in here. So now if you do the same thing, and now because this end is fixed, that's why you see that behavior. So again, in this exercise in here, oh man, I just did 2 of them or 3 of them. Now it's going crazy. That's why you're supposed to play with this thing and see what's going to happen. Okay, so let's reset everything and stop and just pause it like this and you go back. Okay, stop sharing the screen. Let's share the application. Okay. So that is basically the part. Same thing, the drawing in here, the drawing in here. If you have access to a commenting tool, all PDF files have commenting capabilities, okay? Comment, you open the comments and you choose a proper tool for it. Let me see if I can draw it with the pen now. Using my actual pen in here, how that's going to look like. Okay. Same thing in here, and I can write whatever I want to write in here, that the wave is traveling to the right, okay? And I can describe its amplitude in here. This is what the amplitude being 0.77. This pen is no good. I think the mouse now when it comes to writing is better than the pen. Close. Again, you're supposed to write the behavior after it reflects and describe the whole thing in here. Keep it only in the first and the second, because as I let it go earlier and then it reflected off of the other side, that's going to be more than what we need for these questions. Okay. Now, again, we're going to use now an oscillate, not impulse. We're going to choose oscillate with a fixed end and with the damping being none and the amplitude 0.75 and the frequency is exactly 3 Hertz. And once ready, start to play. Okay, you have to be careful, okay, in this case too. You have to just give it enough time and stop it, pause it, so that, and try to do it in slow motion, okay? So observe the wave again when it's moving to before the first reflection, so when it goes to the left. And then after it reflects, because then you're gonna have standing waves. It's gonna be a nightmare trying to keep track of it if you let it go too much, okay? After, and then you go description again, okay? Same thing in here. You're keeping everything except now it's a loose end, not a fixed end. Same thing. Now it's repetitive. You guys see the pattern, okay? Question 7. Compare the behavior of waves on string when the end is loose or fixed. Consider the amplitude, wavelength, and frequencies and point-to-point motion. The key difference between them is the reflected is actually out of phase. It's flipped back for the fixed end and it stays in phase when it comes to the fixed end. That is the key difference between them. Everything else should be the same. Okay. Now, for this part, you're going to pick up the ruler and the timer on slow motion because you really need to keep track of actual measurements in here. Note that the timer stops when you stop the play. I already showed that. Start with the play stopped, measure the length of the string L. So all you have to do for this part is, let me stop sharing and go back and share with you the screen, is first of all, we're paused, so we're good. We're changing it to here. We're changing it to fixed, probably, okay? And since it's we're going to change this one to 3 Hertz. They told us to do that. And the damping is none. The tension, keep it as is. We were not to ask about it. So we'll need the ruler and we need the timer. And let me reset the timer because the timer was on the last value that we had in it. So we need to reset it back to 0. We have everything 0 now. Everything is fixed. At this point, I can use the ruler and find exactly how long this portion of the string is, okay? So I'm hoping you guys will come up with an estimate of how long this portion from green to green on the string itself. We don't care about anything else. We just care about the string. So that is L. You need L for that part, okay? Do we need the amplitude? Probably not. So I don't know why we need this in here. I cannot even get rid of it. Either we get through both rulers or no rulers whatsoever. Okay. So that's going to give me L. Is this straightforward, isn't it? So what is the share button in here? Good.
Yeah, we're good.
So now, make sure you're in slow motion though, okay, not in fast motion, because you're going to take the time it takes for it to go. Now, for the fixed end string, find the frequency. So you're going to play with the frequency. That is your job now, so that you will have the middle of the string fixed. So if you make the frequency, first of all, it's 3 Hertz right now, okay? If you change the frequency, it has to be less. So try to move it small and see when can you get 2 basically empty notes and a node in the middle. I know the ends are fixed because that's what it is. It's a fixed string, okay? The 2 ends are nodes. We need the middle somewhere where that is going to be fixed. You will find difficulty find it when it's exactly fixed. But if it's close enough, that is the value for the frequency in this case, okay? But we need to find the time actually. So when you find it close enough, make sure you refresh, meaning you pause everything, you stop everything at that point. start the timer. It's not going to play because it's stopped. And hit the play button in slow motion and watch for the wave to hit the end of the string. That is your time when it's fixed. That is the time it takes for the wave to go a whole wavelength, which is a period in this case, okay? So you find that in seconds. So when you pause it again, by the time it hits the end, that is the time in seconds, okay? That is the time that you're found in here. Change to normal and start the play and describe the wave after it traveling and reflected the wave. Compare the values of the frequency of oscillations to the value of 1 over t fixed. Remember that you found the frequency in here because you changed it from 3 hertz down to some value, okay? It could be 1.2, it could be 0.5, it could be 0.7, it could be 1.8, it doesn't matter. You're going to find a value in there. Compare that value of the frequency to this measured time that you measured with the time clock, with the timer. You should, are they equal? Is the frequency equal to 1 over t fixed? If there is a difference, explain the difference, where it's coming from, okay? Maybe the error in the measurements, maybe because you actually could not find exactly that middle point that is stationary all the time, and that is typical, okay? So that is one question, question 8. Question 9, we're going to do the same thing, except now we go when we have basically 3 points, 2 points in the middle that are fixed. One in the 1/3 and one in the 2/3. We're focused on the 2/3, okay? And of course the 2 ends that are fixed in this case, okay? No, sorry, 1 end is fixed, 1/3 of the way is fixed, 2/3 of the way is fixed, and because this is loose now, so the last one is not fixed. So that end is free, okay? So the end at the end of the string that is attached to a rod is not going to be fixed. So you'll have 3 fixed points in here. One of them where the oscillations are coming from, 1 in 1/3, and the focus is actually at 2/3 of the way, because that's going to give me a full wavelength. That's going to give me a full lambda, okay? So if I want to draw it, let me go back to that commenting tool again. And let me choose a pen and actually use this pen for it. So this is how the string would look like. So, oops. So in here it's free. So it's going to be an open end. And here it's going to be so what we're looking for this point, that is 2/3 of the way. This is 1/3, 2/3, and this is actually the full length of the string. Because this is open now, it's going to go up and down, okay? So this is distance, the full wavelength. So that is actually the time for the period for when it's loose. It's the time it takes for the wave to go from here to there. Again, you're going to move around with the frequency until you find this shape, okay? Remember, it's loose now. It's not fixed anymore. For the loose string, so keep everything same, except now you change it to loose, okay? And you start it. Once you start it, find the time for it to go, once you have this shape formed, to go 2/3 of the way. That is actually the T loose now, okay? And the frequency, you're looking at the frequency, whichever makes this shape possible when it's loose, and compare these 2 values. And again, try to tell me why this period, 1 over this period, is different, if any, from the frequency that you're looking at. That is question 9. Question 10, you're supposed to find V now. Remember, the velocity is just lambda times frequency, okay? For both for both cases, namely question 8 and question 9. And that is supposed to be the velocity of the wave on this string. I know you are not given the tension of the string, so you really cannot compare it to any theory at this point. But at least these 2 measurements of the velocity are 2 different ones. You have the wavelength, which is this distance in this case, which is 2/3 of the length of a string. And remember, you measure the length of a string all the way here, in this case. So the first case, lambda is actually to the equal to the wave, the length of the string. So lambda in this case is the length of the string, and you have the frequency Multiply them together and you will find the velocity of the wave when the string was actually fixed from both ends. Find the length again, 2/3 of the way, that is actually the new lambda. So this frequency is not the same as the same frequency as it was before. So it's going to change because this is a different mode, by the way. Okay. So now you have a different frequency times a different wavelength. That too should be at the same velocity v. Okay. Because it's the same string, same tension. We didn't change the tension. Don't change the tension in all of the situations. Keep it the same value. Okay. It's critical. The string is the same, so its mu is the same. So the velocity of the wave is the same all the way throughout. And the damping, there is none, so we don't care for that. So we want just to compare the two values. Both of them should be equal. If they are not, please explain why they are not. And the conclusion. So that's your lab. Okay. Clear?
That seems simple enough.
Okay, very good. Thank you. How about Harris and everybody else? Okay, very good. Okay, so I'm gonna stop the recording right now. And please, if you have any questions about it, or if something doesn't work, please let me know on it, okay? Thank you. Thank you. Thank you, Micah. Bye.